All right, this is the video recording for Pre-Calculus Semester 2, July 15th class. All right, so today we are going to start Unit 4. All right, we're going to start Unit 4, and that is on trigonomic identities. All right, trig identities. Okay, so to give you a breakdown of this unit in the next day, 2 days technically if you count today. All right, so we have the introduction, we have lesson 4.1 and 4.2 that we're going to cover in this lecture video. All right, and then in class tomorrow or in class on Thursday, we're going to go over lesson 4.3, right? The applications of these identities, really get into it, see if you have any questions. And then we'll finish up this unit with the review and your unit test here, right? So again, I know that this is quick, but that's the beauty of this pre-calculus semester 2 course, right? It's only about 2 days per unit. So let's get right into it here. If we look at trig identities, all right, so the overview for this entire unit, all right, the overview for that is figuring out how do we derive those identities that we've been introduced to a little bit, right? How can we solve them, and how can we use them to simplify expressions, right? We've done a little bit of introduction, so it shouldn't be totally brand new here, but we're going to really look at how and why those are coming to be the way they are, all right? So, again, not a whole lot of information here, but basically this is talking about how do we know things are true, why do we know things are true, and understanding the relationships between them. All right, so looking at identities and proofs, right? Proofs being, how do we know that this is true, right? We are proving that something is true here. All right, so if we look at the overview for unit 4.1 here, okay, identity came from the Latin word meaning the same, right? So that's what we're thinking about. So it gives us clues to the meaning of mathematical identities, right? There are things that are mathematically going to be the same, all right? And it's not like identical twins here, all right? It's not like that, but we're going to look at things that are mathematically identical, similar, or, you know, you could say equivalent would be another way of saying that. All right, so when we're looking at these trigonomic identities, all right, it is a statement written as an equation that says one trigonomic expression means exactly the same thing as another trigonomic expression. All right, so again, those are equivalent to each other. All right, they are equivalent to each other. So that is our identity. All right, and then what we're going to deal with is again this thing called a proof, all right, or verifying, proving that an equation is what it says it is, right? So when we prove an identity, okay, what we're going to do is we're going to find and verify that those two equations or two statements are equivalent to each other or are equal to each other. So that's what this is really talking about here. All right, so if we look at 4.1, all right, they call it overcoming an identity crisis. Sure, right? What is an identity in mathematics? Okay, it turns out it is just an equation that is true for all values, all right? So again, an identity is an equation that is true for all values, all right? And it's really important here to make sure that we understand the difference between equations and identities, right? Equations are true for a set of values, right? Of specific values. Okay, it's going to be specific values that it works for. Versus an identity, like we just said, is true for all possible values. All right, it is true all possible values. So if we look back here at this example from algebra, okay, so you studied the skill that was solving equations or systems of equations. All right, so solving an equation involves finding the values of a variable that make the equation true. All right, so for example here, being asked to solve this for what values of x, is it true that x plus 4 equals 10? All right, and we know that obviously that solution is x equals 6. All right, so that is looking at an equation here. All right. And sometimes an equation can have more than one solution, right? We talked a lot about this, right? Being the positive and negative version of the answer. So -4 and +4 both make this equation true. All right. So like we said, in these both examples, it is a specific set of values or a specific value that makes this equation true. All right. But when we're dealing with identities, we're dealing with something that makes it true for all possible values, right? So, for example, right, we dealt a lot with this one already. If we had x squared minus y squared, all right, that gave us the factors of x plus y and x minus y, because regardless of what we put in for x or y, it always ended up in this form, right? It always ended up in this form, okay? Because it was true for all values, right? All values. All right, if we look at another one, x over x equals 1, okay? This is true for all values, except, of course, this when it's equal to 0, right? We can't divide by 0. And that's a good point to bring up here, right? Identities are true for all values, but there may be slight exceptions, right? Of course, a lot of the times we're dealing with when x is equal to 0 or x is equal to 1, right? But it is still true for almost every value, with, again, the exception of a couple things, right? So like this one where it's not equal to 0. All right. So then when we introduced ourselves to these identities here, we had trigonomic identities, and we had a couple of these where we said sine squared plus cosine squared. We found out that equals 1. Right, we found out that equals 1 there. All right, and 1 divided by sine, okay, 1 divided by sine gave us this cosecant value, right? That's another identity. All right, tan squared is like sine squared over cosine squared. Right? Sine squared over cosine squared. That's an identity as well. All right. Something that might be a little bit different. Okay, we have 2 theta, parentheses, sine squared theta plus cosine squared theta. All right. Sine squared theta plus cosine squared theta. All right. And we said earlier that sine squared theta plus cosine squared theta gives us 1. So 2 times that is going to give us back out our value, or 2 theta times by 1 is going to give us still 2 theta. All right, cosine divided by sine, that gives us cotangent. 2 times secant is equal to what? All right, and that's equal to 2 over cosine. All right, and again, obviously we know that there's multiple variations that we can do, but again, we understand those 6 basic trigonomic functions, and we understand that we can multiply by constants, and that's going to multiply out and make these equivalent expressions, or these different identities, right? These different identities. And what I mean by that is we understand that secant is 1 over cosine. So if we just multiply 2 times by secant, it's still like saying 2 over cosine, right? We understand how those basic manipulations occur. All right, so now that we understand some of the more basic things, we can look a little bit here at strengthening these identity proving skills. All right, we can look at strengthening these. So to figure out some more of these, all right, it wants us to divide each of these terms by cosine squared theta, right? And we did this a little bit earlier. Hopefully you can remember that, but cosine divided by cosine gives us 1. Sine divided by cosine, and both of those are squared, is going to give us tan squared, and 1 over cosine squared is going to give us secant squared. All right. So this is another identity. This is another identity that we can get from using our basic or our original Pythagorean identity. All right, if we did the same thing for sine squared, right? Cosine over sine squared gives us cotangent squared. Sine over sine gives us 1, and 1 over sine squared gives us cosecant squared. All right, and checking that, of course, that's going to be right there. All right, so this gives us another Pythagorean identity. So again, together, all three of these are known as the three Pythagorean identities. All right. And obviously, you know that we can move these around, like we can bring tangent squared to the other side, so it's equal to 1, right? We can move secant to the other side, but in general, right, these are the three Pythagorean identities in one of the forms that you can see them in. Okay, so the next step or the next question you might be asking then is, okay, great, we did that one, but how do you prove an identity? All right, how do you prove an identity? All right, so if you were given an equation that said this, right, sine x over sine x plus cosine x equals tangent over 1 plus tangent. All right, so the steps in order to solve an identity. Okay, well, first off, you have to realize that we're proving this identity, meaning the left side has to be equal to the right side and vice versa. The right side has to be equal to the left side. So what we can essentially do is we have two options, right? But basically, we start with one side, whether it's the right side or the left side, okay? We start with one side, we use the identities we already know, plus some basic algebra, and we write it until one side looks like the other, right? That's pretty much what we do here, right? And as a general rule, though, it is a good idea to start with the side that looks most complicated, all right? So it's easiest if you start with the side that looks most complicated, all right? So I full-heartedly agree with these tips here, so let's take a second to read them out. Sometimes it helps to write everything in terms of the function sine and cosine, right? It 1000% does, because remember, those are the easiest ones we know how to manipulate. Even tangent we can write as sine and cosine, right? So those are the easiest ones if you write everything in terms of sine and cosine, all right? Do not forget your basic algebra skills, okay? Sometimes it is not that difficult. Sometimes it's just about moving things to the same side of an equation, right? So simple skills like factoring and simplification, all right, through a common denominator, right? All of those skills that we've been really, really honing in on, okay, should not be super difficult here, okay? And this is so true. Oftentimes you'll be asked or able to simplify a identity before trying to prove it. But if you can simplify something before trying to prove it, go right ahead, do it. All right. And then that third tip, of course, use the identities you already know. Don't try to find one on the internet or, you know, pull something out of a hat somewhere. Use the ones that you already know. They're in your toolkit for a reason. All right. So those are going to be our major steps there. So if we look at this base Pythagorean identity, right, we can remember how we got this one, right? We proved it using the unit circle, right? So using our unit circle, we were able to verify that this was true, right? We used Pythagorean theorem of a squared plus b squared equals c squared, and we used the unit circle with a radius equal to 1, right? And that's how we got here. All right, so what we can do then is we can look at our other, right? We can look at our other Pythagorean identities. So if we look here, okay, we start with our Pythagorean identity, tan squared theta plus 1 equals secant squared theta, all right? And one of the tricks there was to start with the side that was more complicated. So we're going to start with our left-hand side here, all right, since that looks a little bit more complicated, all right? And the goal is to end up having this left-hand side look like our right-hand side, which shows secant squared theta, all right? So if we click to begin clicking, all right, perfect. We can say that we can put tan squared theta in terms of sine and cosine, right? That was one of the tricks that they recommended. All right, so we turn tan squared theta plus 1 into sine squared theta over cosine squared theta, right? And we still keep the plus 1 there. All right, so again, it was just a basic definition of tan squared theta, so we can replace it. All right. Next step there is we can turn 1 into something that has a common denominator of cosine squared, right? So since we have a denominator here of cosine squared, remember, we can change 1 into cosine squared over cosine squared, because again, if those were to cancel out, it's going to give us this value of 1 here. So we change it by using this common denominator. Then, since we have a common denominator here, we can put them underneath the same denominator, right? Or underneath the same division sign. So we take our sine squared plus our cosine squared and put that over our cosine squared here. All right, now hopefully you know what's coming next. All right, our first Pythagorean identity says that sine squared plus cosine squared gives us 1. So we're left with 1 over cosine squared theta. All right, and then finally our last definition here, 1 over cosine is how we get secant. Therefore, we can put 1 over cosine squared as secant squared. So when we are done, right, we have turned tan squared plus 1 into secant squared using these, I think, 5 or 6 steps here. All right, so we have just proven that identity. All right, if we look at our Pythagorean identities, our next one, okay? The first question saying which side of the equation should you start with? Obviously, the left side looks more complicated. Okay, the left side looks more complicated. All right. So once we've decided which side we're going to manipulate, we now have to make this left-hand side look like our right-hand side of cotangent. Okay. So if we start with this calculation, we have cosecant squared minus 1. So what are we going to turn cosecant into? What are we going to turn cosecant into? And that should be 1 over sine squared theta. All right, because that is a basic definition there. All right, that is a basic definition. All right. Then what we can do is we can use our common denominator, right? So turn 1 into something with a common denominator. So sine squared over sine squared. All right, since they have a common denominator, now we can combine them, right? We can combine them algebraically. All right. Hopefully you can notice what's going to happen here. Hopefully you can notice what's going to happen. All right, so we have 1 minus sine squared on top. All right, and we have sine squared on bottom. Right, we have 1 over, and we have sine squared over sine squared theta. Hopefully it looks kind of familiar. We've got 1 minus sine squared. All right, and I'm sure it'll show you it in a second here, but this 1 minus sine squared is going to turn into a cosine squared. So we're going to be left with cosine squared over sine squared. And the reason that is because, like I said, the original Pythagorean identity that we had, sine squared plus cosine squared equals 1, we can change that around, right? We can change that around, and so we are left with cosine squared is equal to 1 minus sine squared. So we had that on top, we can flip it around, right? And we can replace it, right? So then if we look, okay, cotangent, again, is of course cosine over sine, therefore cosine squared over sine squared gives us cotangent, right? And this is how we could walk through it, right? And obviously, in general, if I were to ask you to prove something, like me in general, right, I would just ask for this step-by-step calculation or this step-by-step manipulation. I wouldn't necessarily ask for the reasoning here, all right? Where you would get asked for reasoning is if it was turned into, if I asked you to explain, right? If I said, show your work and explain your reasoning, right? That would be more like an essay-based question or a multi-stepped question where I asked you to explain each step as you went, all right? But in general, when you're dealing with proofs, a lot of the times you're going to deal with mostly just this right-hand side. People want to see this step-by-step calculation, right? And you couldn't skip steps, right? That's part of the deal too, all right? If it's not obvious, right? If it's not immediately obvious, you have to show it step by step, right? Like how we showed 1 goes to sine squared over sine squared. You couldn't just jump immediately here to this 1 minus sine squared over sine squared, right? You'd have to show it step by step. All right. Looking at another example here, okay? We can walk through step by step to show this proof here. All right, and again, this is maybe one that, we didn't know off the top of our heads, all right, but we found this proof, or I gave you this proof, and I'm asking you to show me how this is true. How are these two equal to each other here? All right, so again, with this proof, we're going to start with the left-hand side because it looks more complex than the right-hand side. All right, and again, you can start with the right-hand side if you wanted, okay? Doesn't really matter. That's the whole beauty of proofs. They're going to end up equaling each other. But for me personally, this this left-hand side is going to look a little bit more complicated because obviously when we do the foiling, all right, we get these little products here, all right? And again, per usual, this is true because of this proof right here that we know, right? This proof right here that we know, or we just FOIL these two out, right? So we could have written it using this proof, or written the two products, or I'm sorry, written the two factors, so, sine x plus cosine x multiplied by sine x plus cosine x, all right? And write those and FOIL it out, and we would end up with this right here, all right? Now, what we can do here is all we did was change the order, right? All we did was change the order. So, showing that we have sine squared x plus cosine squared x plus 2 sine x cosine x. All right, and again, the reason that being is because in our right-hand side, this 2 sine x cosine x is a term on its own, and it's at the end. So why not just move it to the end there? All right. Then what we can figure out is, of course, sine squared x plus cosine squared x gives us this value of 1. So we replace both those values, and lo and behold, our left side equals our right side. All right, and we have just proved another identity here. Okay. So if we do this practice here together, all right, again, it is going to be similar. It is going to be similar every time. All right, and to me, the right-hand side is more complicated, okay, than our left-hand side. So if we begin this, we're trying to make our right-hand side equal to our left-hand side. So this is asking us, what is this going to be equal to? All right, so if I have my cosine and cosine, cotangent, right, what is cotangent equal to? It's not sine over cosine, it's cosine over sine. All right, so cotangent is going to be cosine x over sine x. So that's what my expression turns into when I turn everything in forms of sine and cosine. All right, then remember, when we divide by an exponent, it's like multiplying by its reciprocal. So this is like saying multiplying by its reciprocal. So instead of cosine over sine, it's going to be sine over cosine. All right, when we look at this here, we have cosine x on top, cosine x on bottom. So those guys cancel each other out. And we are left with our left-hand side looking like our right-hand side. All right, this proves this identity here. All right, and there's one specific thing here. Remember, we talked about we talked about identities can have a little bit of constraints here. All right, and the reason we have a constraint is note that the identity is only valid on the domain of cosine x over cotangent, which is given by x cannot equal n pi over 2. And again, the reason being is because it is undefined. This function becomes undefined at these values of x, right? Because that's where we have our vertical asymptotes of our cotangent function, okay? So, and that occurs where it is undefined, right? Where this expression cotangent is undefined, okay? And again, it occurs at these multiples here, all right? So those are good things to always keep in our heads here. All right. Moving forward with our another practice here. Obviously, the left-hand side looks much more complicated than the right-hand side. All right, so when we look at our beginning calculation here, all right, we're going to try to turn everything in terms of sine and cosine. So we know cosine x, we've got secant x. Okay, we've got secant x. All right, and secant is 1 over cosine. Right, 1 over cosine. So I've got cosine x, 1 over cosine, and obviously cosecant is 1 over sine. So I'm left with cosine x over 1 cosine x, and sine x over 1 sine x. All right, and Again, they skipped a step here, but we know that when we divide by a fraction, it's like multiplying by the reciprocal. So I'm left with cosine x times cosine x and sine x times sine x, which gives us this problem here. All right. And then, of course, we know one of our principal identities here is that cosine squared plus sine squared gives us 1. Therefore, 1 equals 1, and we're done. All right. But something that we're now adding on here are those restraints where this is not true, right? And that would be anywhere where secant is undefined and cosecant is undefined. All right, where secant is undefined and cosecant is undefined. All right, and the reason that is of course, again, at values of n pi over 2, that is where these secant and cosecants are undefined or equal to 0. Right, they're going to be equal to 0. All right, and since secant and cosecant are never equal to 0, the domain is where sine of x and cosine of x don't equal 0. All right, since secant and cosecant are never 0, we're just dealing with when sine or cosine is equal to 0. All right, so again, looking a little bit further, now that we understand how to prove, we now have to fully answer the question, where is this not true, right? Where is this identity or where is this proof not true? All right, so then now we've done some more basic identities, but now we have to deal with what happens if both sides of the equation are maybe a little bit more complicated, right? That's what they're saying, working both sides of an identity here. All right, so we can look at both of these, all right, because it's a little bit difficult on both sides. All right, so when you're dealing with this, you can pick either side of the expression to work with. Again, personally, I picked the one that looks a little bit more difficult, and it looks like they're keeping that in trend. So they picked the left-hand side here. All right, so if we look at this, all right, so when we're dealing with this, we have to find a common denominator between both of the factors on the left-hand side. All right, so we have to multiply it so we have that common denominator. Once they've got the common denominator, right, we add our numerators together, and this is the expression that we are left with. All right, this is the expression that we are left with. All right, secant x minus 1 plus secant x plus 1. All right, then what we can do is simplify our numerator and simplify our denominator here. We can simplify both, right? Luckily, this bottom here is a perfect square, right? It's a perfect square, so it simplifies to secant squared x minus 1. All right, and then our top here, our 1 and our 1 cancel, so we're left with just 2 secant x. All right. Okay, and one of our identities here deals with secant squared x minus 1, okay, and that'll give us tan squared x. All right, so we now have 2 secant x over tan squared x. All right, now that we've got it in something a lot more simple here, we can turn both of these into things in terms of sine and cosine. All right, in terms of sine and cosine. So again, we just use our definition for secant, which is 1 over cosine, and since there's a 2 there, it's now 2 over cosine. All right, and tan squared x is sine squared x over cosine squared x. All right, and now what we know, again, is when we divide by a fraction, it's like multiplying by its reciprocal. So we have cosine x on the denominator here and cosine squared x in the numerator. So we can cancel out this cosine x here, and this now, instead of being cosine squared, is now just cosine x. All right, so we now have 2 cosine x over sine squared x. All right, and what we can do is you could either stop there if that's something, or we can get rid of one of these signs here. So again, it's only in terms of sine and cosine, not sine squared, right? We can change cosine over sine into a cotangent. We can change cosine over a sine into cotangent. So we're left with here 2 cotangent x over sine x. All right. And again, personal preference here. Okay, if you're trying to prove this, you just have to make sure the left-hand side equals the right-hand side. All right. So I personally might have stopped here for the time being and then started working on the right-hand side, or again, they keep going with it, which is totally fine, right? As long as you get the left-hand side equaling the right-hand side with with using proper mathematical expressions. That's all that really matters here. Okay? But now that we've gotten our left side simplified here, we now have to start simplifying our right-hand side. Okay, we have to start simplifying our right-hand side. All right, so again, as it says here, we simplified our left-hand side down to this 2 cotangent x over sine x. Now we have to turn our right-hand side into this final expression here of 2 cotangent x over sine. Okay, that's the next step here. So then, all right, so then what we can do is turn everything in terms of sine and cosine. If you have no idea where to start there, okay? And once we start there and we start changing things, okay, when we divide by expressions, we now know we multiply by the reciprocal. Okay, we multiply by the reciprocal. All right. The other approach here, since again the reciprocal is not an easy number to deal with in this case, okay, we can look at what do we need our numerator to become? What do we need our numerator to become? And by that I mean, if you look at this proof that we're trying to solve, we need this top to be 2 cotangent x. Well, I've got the 2 value there, but I've got 1 over sine x. So I need to turn that into a cotangent. So what I can do is I can multiply my entire expression by cosine over cosine, because essentially I'm multiplying it by 1, right? That's what cosine x over cosine x is going to give you a value of 1 here. So I can multiply this in order to get cosine over sine on top, right? Or again, eventually we're going to simplify that down to cotangent. All right. But an also added benefit here is, since I have a cosine x in my denominator, okay, that will cancel out with the cosine x over here, right? That will cancel out over here. All right, and again, go step by step with your cancellations so you can always check if it doesn't seem like it should work. All right, but this cosine x goes up here, and this cosine cancels with this one down here. All right, so now I've got cosine x and sine x on top, and I've got 1 over sine x minus cosine squared x over sine x. All right. Ooh. Okay, so then what we can do is, these are already in terms of common denominator. All right, so we can combine them. All right, and same thing. We have cosine over sine, then we can rewrite that as our cotangent. So our numerator is in the correct form that we need it to. All right, our denominator, we've got to change a little bit more. All right, so once we've combined once we've combined our denominator here, we're left with this expression 1 over cosine squared x over sine x. And hopefully, again, this is starting to look familiar. 1 minus cosine x, we can change that into sine squared x. All right, we can change that to sine squared x because of our Pythagorean identity that we are already familiar with. All right, now I've got sine squared x over sine x, cancel out one of the sines, and I'm left with my 2 cotangent x over sine x. All right, therefore, we have finally proven that the left side equals the right side, since they both can be reduced down or changed into this 2 cotangent of x over sine x expression there. All right. And as one of the rules or hints we talked about at the beginning here stated, sometimes it's easier to simplify before we try to start proving. All right, sometimes it's easier to simplify before we start proving. All right, so for example here, if we do our cross multiplication, right, we do our cross multiplication. So I take sine x times by 1 plus tan x, and I multiply my sine x plus cosine x times by this tan x, right? I do this cross product multiplication. All right, this expression is equivalent to this expression here. All right, again, key there, only when both expressions are defined, right? Only when both expressions are defined, meaning this can't equal 0 and this can't equal 0. Okay, so once we have done that, okay, we then can start our proof, all right? Because it's always easier to not have to deal with fractions, in my personal opinion, all right? So once we've gotten it in this form here, we can then start with either side. And the right-hand side has this tangent function on the outside, so let's just go there, right? If we turn tangent into sine over cosine, all right, based on our reason of definition, all right, then we can distribute, okay, we can distribute our cosine, or 1 over cosine, to both of these factors. The reason being, look at our original expression. We have sine x on the outside, so let's leave sine x where it is. Let's distribute the cosine x, all right? And lo and behold, sine x over cosine gives us tangent, cosine over cosine gives us 1, and we have proven our identity in only 3 steps here. All right, we've proven our identity in 3 steps because we took the simplification route. We just easily changed it right off the bat. Okay. Now let's look at how do we prove if something is not an identity. All right, if we prove something is not an identity. So if we look at the expression cosine x plus sine x plus 1, okay, this is not an identity. All right, we can prove that using mathematical expressions, or what we can do is we can look at graphically. We can look at it graphically, all right? Because an identity has to be true for all values, right? We said that an identity has to be true for all values. So if we look at this graphically and there's one value that does not match up, it's automatically not true. It's not an identity. So we could pick any point along this line, but basically notice the 2 graphs don't match up perfectly. They're not right on top of each other. Therefore, it is not an identity. If I asked you to use a specific point here, look at where x is equal to 0. All right. The expression is equal, or sorry, it works for x equals 0 here, right? They're at the same point. But if we look pretty much anywhere else except for the intersection points, right? So let's look at pi over 2. Okay, at pi over 2, one of these expressions right there, okay, is equal to 0. Cosine is equal to 0, while sine is equal to positive 2. So therefore, it is not an identity. Okay, and using this type of argument is referred to as finding a counterexample. All right, and it is an example where it proves that the statement is false. Right, so counterexample. Right? It is an example that proves the statement is false. All right. So if we review here, right, we have trig equations that we can use, right? We have trig equations that we can use. And then within that, we have these identities. All right. Equations are where they are true at the points that we're looking at, or for a set specific values. Identities are where they are true for all values in the domain, or all values of x have to be true in order to be a trig identity. Okay, so again, looking at the study guide, I can't harp these enough. They're going to be your best friends here. Understanding these identities here, all right, understanding these identities, and we walked through all of these answers already, so I don't want to take too much time here, all right, but it is always best to start with the most complicated side, all right, and if both sides are complicated, well, then you know you're going to simplify both sides, so start with whatever one you're feeling like, all right, and again, the calculation is the biggest part here, going step by step, showing each individual process, right? As long as you know the reason, that's all that matters, right? I would never ask you for this except for, again, of course, those expressions where I'm asking you to explain, or I'm telling you to talk me through your thought process here, all right? But definitely going step by step is the big key here. Okay, and on all of these we already walked through, so like I said, I don't want to spend too much time here, but make sure that you go through those on your own and can do them logically, all right? And then the last couple things here, all right, so a counterexample, okay? A counterexample is where you have a value that doesn't satisfy our equation, right? a value that doesn't satisfy the equation. All right, it has to be every value, right? Every value in order to be an identity. So if you look at page 11 here, or this here, every identity is an equation, right? Every identity is an equation, but not all equations are identities. All right, every equation is not an identity. All right, but every identity is an equation. Okay, so identities, you can always plug in values, solve, and see if it's true. All right, and it has to be true, of course, for all values in order to be considered an identity. All right, moving forward here with the checkup, of course, it's going to be a great thing for you to do at least a couple of these worked problems here. All right. 1 through 5, hopefully pretty easy. Identify it as an identity or not an identity. And you can do this numerous ways. One, if it's an identity that's offhand, like this first one, you should start to get familiar with these because obviously they're going to be in your tool belt. All right. But if they are not familiar to you, you can plug them in graphically, see if they match up everywhere. All right. Or you can just look for values where it may or may not be true, right? Look for that counter example here. All right, here is really, really nice. Okay, it's showing you the reasons for how you get from one part to the next. All right, it's even telling you start with your left-hand side, right? So start with the left-hand side, follow this reasoning here. All right, follow the reasoning, and hopefully this should start to get a little bit more helpful here, because then when you get to problems like this, right, it's going to ask you to do that on your own without the guided reasoning here. All right, and then something like I said, this would be like an essay question. Explain. All right, explain. So tell me the reason. Why does this work? Why do each of these steps work? All right, and again, my personal suggestion, at least do 1 here. Maybe 2, since there's so many. Do 2 there. Do 2 where you've got the reason. All right. And then 14 through 20 is, of course, going to be the biggest test for you. Can you do the step-by-step calculation, and can you tell me the reason as to why? If you can do 14 through 20 without any major hiccups, you're going to ace this test here. All right. This quiz and this test, right? This is a big chunk of this unit. Right, so understanding those is going to be helpful. All right, obviously you have this one quiz here, so once you get through, the practice problems in the unit and then the checkup, please go ahead and do this quiz here. All right, so then the other one is lesson 4.2 here, so even more with those trig identities, all right, even more with those trigonomic identities here. So looking at this here, all right, obviously we are familiar with that first Pythagorean identity, all right, and we found it really useful, especially with our proofs here, all right, but another good thing here that we can do is we can use this trigonomic sum identity, all right, and what that looks like here is looking at if I have cosine or sine or tangent of a plus b, all right, it can give us a value here of another identity here. So if we look at cosine specifically, since that's the one we're dealing with, all right, cosine of a plus b, all right, it gives us cosine of a cosine b minus sine a sine b, all right. And we have versions of that for sine and for tangent here, all right? But if we look at, obviously, the name sum, all right, and the reason that is because we have a plus b, so it's the sum of 2 angles together, all right? Now, in order to build this formula here, okay, we've got to remember our definitions based on the unit circle, right? We've got to understand this Pythagorean identity. That's our new BFF here. And then we've got to understand that we can write the distance between 2 points as this, all right? And this is looking at the total distance here, all right? So we take the difference between our x components and we square them. We add them to our difference between our y components that's squared, and we take the square root of that, right? So again, thinking a squared plus b squared equals c squared, right? We are solving for one of those, right? And in order to get our a and our b, we have to take the difference between the 2 points. All right, we have to take the difference between the 2 points. So let's take a look here to identify our trigonomic sum identity for cosine. Okay, so like I said, looking at our unit circle here, we can look at what happens if we have our angle A in green and we have our angle B in blue. All right, we can look at our different angles here. All right, and we could also look at angle B by itself, right, as just negative B. When we're doing our derivation, sometimes it's good to know that. So if we look at our points, P1 to P2, right, is angle A, P2 to P3 being angle B, and then P1 to P4 is negative angle B. All right. So if we look at this, right, we can look at it in terms of just cosine and sine here, right? So we can rewrite our coordinates in terms of cosine and sine. So obviously, if we look at angle A here, okay, we know our x component is cosine and we know our y component is sine. That's based off of our unit circle identities here, all right? But now what we did is we still have cosine being x and sine being x, but now it's angle A plus angle B, right? So that's how we get here. Angle A is our original, but now we've also added on this angle B, right? Because if we just went straight here, this would of course be cosine of this angle. But since B is only the distance between A and B here, this green line and this blue line, we have to do this addition property here. All right, we have to do that addition property here. All right, so as I just told you, right, the total angle measurement between P1 and P3. All right, P1 and P3. All right, is the total angle there. All right, that's our total angle, A plus B. All right, so we have to look at, of course, the different line segments that connect these points. All right, and if we look at our distance equation here, right, distance being the difference between x1, y1, and x2, y2, right? So if we look at this expression here, right, we can start replacing values, right? We can start replacing values. So again, if we think about P1 here as our x1, y1 coordinate, right? So x1 was what, x1, y1, versus x2, y2 being up here, right? Being up here is our cosine A plus B sine A plus B. All right, we can look at this purple length, right? We can look at this purple length between P1 and P3. Okay. So we can distribute out, right? We can distribute out those values. Then we can simplify, right? We can simplify as being the set of the two equations equal to each other. All right, the set of the two equations being equal to each other. All right, and if we use our mathematical operations, okay, of course we can obviously get down to a more simplified version. I know it takes a lot of steps here, and I'll let you explore those on your own, okay, but we end up with this expression here. Again, all we're doing is combining like terms and then using basic mathematical principles that we're really familiar with by now. All right, but we're given this expression. All right, oh, sorry, I went a little bit too far there. All right, we're given this expression. All right, we're given this expression here in terms of this value 2. Right, we're given it in terms of this expression 2, and what we can do there is we can simplify, right, to an identity in terms of just A and B, right? We can simplify down in terms of A and B. All right, so again, really take some time to walk through that on your own. I know that was quick here, but this section here is a little bit more meaty. All right, so I want you to make sure you take some time here on your own. All right, but if we look at cosine A minus B, right, if we look at the difference identity, obviously difference because we're subtracting the two now, okay, we can do a proof here. we can do a proof here to prove that cosine A minus B is going to give us this equation on our right-hand side. All right, so we can look at a proof here. If we want to avoid our unit circle, we can look at proving using our identities here. So if we start with our our right-hand side. Apologies, it was left-hand side. If we start with our left-hand side here, okay, we know that we can separate this out here as being cosine A plus a negative B here. All right, and we can use our identity that we just developed for cosine of A plus B, right? We can use our identity for cosine of A plus B, right? Except now we just replace the positive B, right? Since it's a plus, all right, we replace it with a negative B here. All right, we replace with a negative B. All right, and since cosine is even, right? Cosine is even. Remember back to those definitions of even versus odd. So since it is even, right, it's the same on both sides of our y-axis. It makes it even. Therefore, negative b is going to be the same value as positive b, right? That's the beauty of symmetry. All right. But sine, remember, if you think about the left and the right-hand side of our equation here, was odd. It was odd. So because it was an odd function, this negative sign is going to affect the sign overall. So negative b becomes negative sine of b, right? It becomes negative sine of b. All right. So what ends up happening is we end up bringing that negative sign to the forefront, right? And negative cancels with negative and it becomes positive, right? It becomes that positive value. All right. And then we are obviously left with our new proof here, right? We are left with our new proof here. Okay. I would obviously say the left-hand side of this cosine identity is more complicated. All right. So again, looking at this guy here, this would be a more complicated side. So we're going to try to change cosine of pi over 2 minus x into our sine over sine of x here. All right. And so what we can do with this identity here is we can obviously separate it out into two parts. Right? And we would use our brand new identity that we just developed in order to find this answer here. And I don't expect you to know this reason offhand. That's why those study sheets are super important, okay? But using this new identity that we just developed here, we know that this angle is A, this angle is B. So we rewrite it, and instead of putting A and B, we just put our brand new identity that we figured out, all right? And now, since we have this, we can simplify even further, right? We can simplify this down even further. And the answer for that is going to be C, because we can substitute cosine of 2 over pi, right? Because that is going to give us a 0, right? If we go to our unit circle, pi over 2 gives us a 0 here. Right? And sine of pi over 2, right? So if this is our cosine value gives us 0, right? Our sine value gives us 1. And think about our unit circle here, right? Pi over 2 is that 90-degree angle, all right? So at that, my x coordinate is 0 cosine, and my y coordinate at 90 degrees is 1 on my unit circle. So that's what I am left with there, okay? So then obviously 0 times cosine gives us a 0 here, and we're just left with sine of x, right? And then obviously we were able to figure out that that is our right-hand side of our equation, so we've made both sides equivalent. Right, we've made both sides equivalent. And right here, we've noticed, all right, we've already proven that multiple times graphically, because if we plug in both of these functions, right, y equals cosine pi over 2 minus x and y equals sine x, you're going to notice that they're the exact same graph, right? They will overlap on top of each other if you were to check these in graphically. All right, so that's another way we could look at that. All right, and of course, we can do the exact same thing for sine and for tangent, right? We can do the same thing for sine and for tangent, all right? We can do the combination and the difference between them. Okay, we can do the combination and the difference between them. All right, and we can derive them and figure out why is this true. So if we look at our calculation for sine A minus B, all right, this is like saying A, or I'm sorry, if we try to change sine of A minus B, this is like saying A plus a negative B, right? Then we can use our identity here up here that's already identified, okay, already identified. We can replace the values here, all right, and then we, like I said, we said earlier, since cosine since cosine is even, this is like saying sine A cosine B, but since sine is not even, right, it's odd, this is going to carry that negative sign out. So we're going to look for that guy there. All right, again, because cosine is even and sine is an odd function. All right, so therefore, once we've gotten to that point, we have just proven this new function, all right, this new identity here. All right, and again, we did skip over how did we get this proof and how did we get this proof, because it, like it says here, you can derive it by a similar method that we use to derive cosine of A plus B. All right, just for the sake of time here. All right, then same thing. Obviously, we want to start with our sine expression here. So when we begin this, all right, this is like saying what? This is like saying what? And apologies, I don't have my my new derived equation offhand, so I'm gonna I think it's this one. Oh, I was close. Apologies. All right, but this is my new expression here. All right. Oh, and I should have known. Key here, right? If you start with sine, the expression starts with sine. Right? If it started with cosine, the expression started with cosine. Miss Judy, I should have known. All right, but apologies, you would have had this on hand here. All right, but if we continue, we can plug in our values for sine at pi over 2 and cosine at pi over 2. And again, remember, pi over 2 for this specific example is at 90 degrees. So our sine value is our y value. So that's going to give us a 1, and this is going to give us a 0. So it's going to be 1, 0. All right, we substitute those in. All right, and then obviously 0 times sine of x just gives us cosine. So that's how we get there, right? And again, obviously we've already proven this, and you can prove it graphically by plugging both of these in and making sure that they overlap. All right, and then we can do tangent the exact same way. All right, we can do tangent the exact same way. All right, using the identity for A plus B, we got to this new expression here. All right, and tangent, we have this negative value. So this is the real question is what's going to happen with tangent? All right, well, regardless of whatever happens, it has to be even, right? It has to be even. So if this negative is to come out, it would have to come out on this side as well, right? So anything that does not have the same properties, right? So this one was positive and this one was negative. It would not be that one. It's got to have the same thing happen to it. So, right? If I carry this negative out, I also have to carry this negative out. So this one becomes negative, this one becomes positive, right? And the reason I knew that we were going to carry that negative sign out is because tangent is also an odd function, right? It does not have symmetry across the origin, right? It does not have symmetry across the origin, all right, or across apologies, it has symmetry across the origin. It does not have symmetry across our y-axes, right? So they look different on the left and the right-hand side. So therefore, it is that odd function, all right? And once we just carry that negative sign out, we have proven our identity there for tan A minus B. Okay, so then the question becomes, what's the use of these identities? Okay, why would we use them? All right, so looking at this expression here, okay, some of these can't be solved by hand, all right? So if we were trying to find the exact value of sine of 15 degrees, all right, those are ones that we don't know offhand. So a really simple thing we can do is, well, we know what 45 is and we know what 30 is. So we can subtract both of those, right? We can subtract both of those, right? And since we know those values, right, we know those values, we can just plug them in to our new expression here, right? Again, if I walk you through this process, we replaced our angles and we got this equation right here. Well, we know that sine of 45, right? Sine of 45 is square root of 2 over 2. We know that cosine of 30 is square root of 3 over 2, right? So all we do is we plug in these values for angles that we already know, right? And it gives us this simplified expression. And I know it doesn't look simplified here, right? But if you were to plug into your equation sine of 15 degrees, it's not going to give you out this expression in terms of exact values. It would give you out some decimal, right? It would give you out some decimal. And again, when it's asking for exact values, you cannot round it, and that's kind of a negative, I know, right? But that's why this identities here, these that we just worked with, are going to be super helpful. All right. And again, of course, as always, you can check this. You can check what you know, right, by plugging this in, getting a value out in your calculator, and then also plugging in sine of 15 degrees and seeing if it matches up, right? You can always do that as well. As long as you're in the right mode, you're in degrees for your graphing calculator. All right. So looking here, these are our trigonomic identities that we were just dealing with, right? And we were just proving. Okay, so these are going to be some that you can use under your belt here moving forward. All right. So again, if we were to look at these, and I'll let you guys look through these on your own and take some time to digest them, right? But we don't know what some of these angles are, and we already looked at the sine of 15 one here, right? But maybe let's look at this guy. So we don't know, right, what sine of 75 might be. All right, but if we look, okay, we know that 75 is 45 plus 30, and we know what both of those angles are. So we can then plug in what we already know and solve. All right. Or oppositely, right, if we have sine of 60 and cosine 45, if we look at our solution here, right, we look at our solution, that's telling us that we're looking for those two added together, right? It matched up with the expression, so this is telling us this is how we would solve for sine of 105, right? That's telling us we could solve for sine of 105. All right, and again, for this one here, it's going to be matching up the equations, right? Matching up the equations with the trigonomic identity reference, right? That's the key here. All right, then we can deal with something that's called double angles. Double angles, all right? And it's doubled because obviously it's multiplied by 2. So it's like if we had this angle here for x and we just multiplied it by 2. So it's a double angle identity. All right, so it's like saying A is equal to B, so therefore this is just saying cosine of 2A. All right, and if we look at cosine of 2a or 2x, right, we use what we know, right? We use our identities that we know, so this is what we are left with. It's 2 cosine squared x minus 1, right? 2 cosine squared x minus 1. And if we follow through with the similar proofs for sine and tangent, we are left with those expressions there that you can see. All right. So we can do that as well. All right, and obviously here, if we notice that there are multiple forms for cosine squared x, or sorry, cosine 2x, all right, and all of those forms will work. Now, which form we use, of course, is dependent on the problem that we're trying to solve here. All right, so looking at our double angle identities here, if we have sine of x is equal to negative 5 over 13 and x is in the quadrant 4, find sine 2x, cosine 2x and tan x. All right, so we says it's in quadrant 4. Okay, so that's going to be super important because you've got to remember our identities here. All right. And up here it's saying start by looking at all the double angle identities you can see. Ooh, apologies. read too slow. And seeing which ones you can already solve immediately. So we know that sine x is equal to this, right? So looking at our double identities, what can we solve already, if anything, right? What only uses sine of x? What only uses sine of x? All right. And we notice here, right here, this second version, all we need is sine squared x, right? We need sine squared x. So since it only dealt with sine of x, right, we can use that identity, right? We can use that identity. All right, and again, remember, this is sine squared x or sine of x squared, right? So we just plug in this value for our sine of x, and we square it to get out our cosine of 2x. All right, so again, we used this form because we were given sine x, and this is the only one we can solve for because it's the only value that deals with sine of x. All right, but now we have sine of x, we have sine squared x, right? We have sine squared x, or we can calculate sine squared x, and now we have cosine of 2x, right? So those values are under our belt here. All right, and if we look, we now know that sine of 2x is equal to 2 sine of x cosine x, right? That's our equation here. All right, so what we can do then is go back to our unit circle, and we can look at, we already have sine of x, now we need to figure out what cosine of x is. All right, and since sine of x is equal to the vertical coordinate of the terminal point, right? I know that's a lot. Basically, it's saying, right, it's equal to the y coordinate. All right. Okay, we were told that our angle is in quadrant 4, and this is where it becomes super important because we are now not dealing with this side of our unit circle. We're only going to deal in quadrant 4 here, so that makes it pretty easy for us. We know we're going to deal with this angle right here, all right, where our y coordinate is -5/13. Right, so we know that on our unit circle, our radius is 1. We know that we are at -5/13, right? That's where we're at with our y coordinate. So now we can solve for cosine of x. Right? We can solve for cosine of x here just using our Pythagorean theorem. All right, so we have our value of -5/13, we have our radius of 1, and we can then solve for cosine of x, right? Once we've solved for cosine of x, all we have to do is plug in our two values there and then solve using algebraic skills, right? So then we have our sine of 2x, right? So far we have calculated cosine 2x, sine of 2x, right? We have our value for cosine of x, we have our value of sine of x, and so hopefully when we get to tangent of 2x here, if you look, we just have tan of x and tan squared of x. So let's see what we're going to do here. Obviously, tangent is a function of sine and cosine. All right, so since we have that, we can just replace tan of 2x is just saying sine of 2x over cosine 2x, right? We can take those values and we solve for tangent of 2x. All right, so again, not hopefully too terribly difficult in terms of algebraic skills, right? It's all about just logic, using what you can logically to solve your problems. All right. Then on the opposite side, instead of doing double angle identities, we can look at this thing called half angle identities. All right, and again, this is going to become really important when we're dealing with calculus here, but we can now look at half angle identities. All right, and the double angle identities already show us this relationship, luckily, right? All we have to do is rearrange them. Okay, so if we rearrange them here, we can then see this different identities here. All right, so oh, sorry, I lied to you. First off, this is we have obviously the half angle identities, and then we also have the squared identities here. Apologies. All right, the squared identities are the ones that we rearrange here to get these equations, and that's in terms of sine squared or cosine squared. All right. So apologies there, but that's our cosine squared and sine squared. Those are our squared identities here, obviously because the left-hand side is squared. All right, with our half angle identities, all right, this is going to have obviously it being divided by 2 like I was talking about. So if we look here with our squared identities here, all right, we can take the square root of both sides to get sine by itself, right? And then all we have to do is substitute in, instead of x, we write in x divided by 2, right? Because it's obviously half of the angle, all right? And when we do that, we get x over 2, and instead of having 2x, we just have x by itself, all right? And we can do the exact same thing for cosine. And that gets us to these half angle identities here, all right? And we can look at trying to solve them, or using these half angle identities to solve for different values here. So again, cosine x is equal to 3 over 5, and x is in the 4th quadrant. What is cosine x over 2? All right, you would obviously use this cosine x over 2 equation. We know that cosine of x is equal to 3 over 5, so we would just replace and replug in. All right, so our two values here are going to give us positive and negative 4 over 5. Positive and negative 4 over 5. All right, but it told you we are in quadrant 4. We are in quadrant 4. All right, so cosine is if cosine of x is a positive number, the angle can be in either quadrant 1 or quadrant 4. All right, and since it says it's in quadrant 4, right, we have to deal with the negative solution. All right, we'd have to deal with the negative solution. All right, and again, that's what knowing these quadrants are going to be super helpful for. Quadrant 1, 2, 3, 4, right? So again, we got a positive and a negative value, all right? But since it's explicitly told us we were dealing in quadrant 4, right? We have to look for the values that are going to match that up with, all right? So this one is the same problem here, except it's asking you dealing in quadrant 1, right? So if we were dealing in quadrant 1, all right, it would look the same, right? We could plug it in, it would look the same. But our value would have to be positive here, right? We'd have to have the positive value because obviously we're dealing with quadrant 1, and our cosine value would be our output, right? So again, it's not just solving the equation, it's solving and then double checking against what you know, what you have, and what you need, obviously. All right, so then I know it's been a lot, and I'm glad they said that too. It's been a marathon of new formulas, but you're in the last lap, all right? So this final one is called product to sum identities, all right? And the reason that is because obviously we go from having the product of 2 multiplied together to giving us a sum, all right? So if we take a look at this first one here, all right, so we have cosine A times by cosine B equals 1/2 cosine A minus B plus cosine A plus B, right? Really large and long, I know. But the reason that is because if we look at cosine of A minus B, this was that identity we looked at in the beginning, right? Same thing here, A plus B, this was that identity. So all we had to do was, instead of writing cosine plus cosine, we replaced them out. All right, and as you're going to notice here, we have a minus sine AB and a plus sine AB, and those end up canceling each other out. Then we can combine like terms here. So we have 2 times cosine A cosine B, all right? And then obviously if we want to get this by itself, we just divide by 2 on both sides. So therefore, we are left with this final identity here. All right, and again, the same thing for sine, cosine, sine and sine, sine and cosine, cosine and sine. All right, it's the same things here. All right, not too terribly difficult here, hopefully. All right, and again, the trick is not really the derivation here. It's utilizing the identity once we understand the derivation. All right. And then the final set of practice problems here. I think the left-hand side is more complicated, and so do they, so we would start there, right? And what we would do is we'd multiply out the terms, okay? And then we have sine squared x and cosine squared x. So that's going to give us a value of 1. So I'm going to have 1 plus my value here, right? 1 plus my value there. So then I can continue. And if I use the product to sum identity, right, of cosine and sine, okay, of cosine and sine, I can rewrite as this, all right? Then by using, by using algebraic simplification, we get to this step here, all right? And then obviously, sine of 0 gives us 0, right? Sine of 0 gives us 0 there. Once we've gotten to this point, obviously we've got it in the same form, and that proves this, right? And I know that this step here is a little bit confusing, or how we get from this step to this step, but once you have your study sheet in front of you and you can look at this product to sum identity, it's super, super simple. All right, again, it is just utilizing what you have, where you need to go, and making the correct substitutions. All right, and this is, oh, I wish they summarized it for us. I thought they did, but we have looked at that. Oh, there it is. Sorry, I missed it. All right, this is going to be your best friend. All right, this is going to be your best friend because there are so many identities that we just really quickly glossed through here. And so again, please take some time to go through those at your own pace here. But this study sheet of summary is going to be your best friend. All right. Again, the trick is going to be utilizing the equations that you have at hand, and now you have a lot of them at hand, including the Pythagorean identities that aren't included on this, right, that we just worked on in the last unit. All right, okay, using this and finding what you need, right? Find what you need and replace where you need it. Find what you need and replace where you need it. Okay, so this obviously you're going to fill out based on this study sheet here and those couple examples that we went through together. All right, so I don't want to spend too long on that. And then looking at your checkup here. All right, looking at your checkup. All right. It's asking you to verify, that's telling us to make the left hand look like the right hand side. Okay, deriving, again, is how did we get to this point, right? Doing a proof. All right, same thing with 3 here. All right, doing the proofs here. All right, now for 4, it's asking you to find the exact value of the following. Okay, so this is where you might have to look at, let me show you. This is where you're going to have to look at things being added together or things being subtracted. Right? Angles being added together or being subtracted. All right? So knowing those main angles, or our reference angles, are going to be super, super important. All right? And then being able to plug back in. All right? Write the products as sums. All right? That's asking us to use those new identities. Right? Use those new identities. So write it in terms of general, then plug in for the values that you have. All right? Really, really take some time with this unit. I know it was a lot of new equations, new expressions, a lot to really digest here, and I wish we had more than just an hour and a half to go through this stuff. All right, but please take some time and go through it. Okay. And then when you feel comfortable and confident, remember you have this quiz here. So you've got 2 quizzes for this unit. Tomorrow we'll address 4.3 and the summary of the unit. Okay, so we're going to try to finish up lesson 4 here tomorrow. Or again, if you need more time with this unit, since it was a lot of equations, remember, I'm not giving you any homework over the weekend for trig. So if you need to extend this into the weekend, by all means do that, as long as it is done by Monday. That's kind of your goal here. Get this done by Monday. All right. Per usual, if you've got questions, reach out and let me know how I can help you guys. All right. Other than that, I'll see you tomorrow for class. Goodbye, goodbye.